All right, let's take a look. So we talked yesterday a little bit. About how we're going to, in general, well, the last few days, but how we can, how we can take any kind of parent graph and tweak it using 4 parameters, right? Real quick, let's write down what is our most general way of writing down a function that incorporates all of the different parameters. So in terms of f of x, g of x would be what? But I mean, we don't want to be specific. We're just going to make this general. We're just going to write this in terms. Forget about this for a second. So g of x equals what? How do I include all my parameters in this in terms of f of x? Where do they go? So a goes out front, good, times. Okay, 1 over b times x minus h plus. Okay, good. Okay. But we started talking specifically about parabolas yesterday. We started to say some interesting things. We said, remember, we talked among other things about how 2 points defines a line, 3 points defines a parabola, right? So if we have 3 points, we could always, by doing a regressional analysis, we're going to get a perfect fit, and we're going to actually fit that curve, right? Okay? And so that's a good trick on a calculator. Let's think about this in terms of the number of parameters required to define different types of functions. How many parameters are required to define a line? 2. What are they typically? What are they? Well, no, that's not what I mean. Parameters are numbers that we can dial in to specify a line. Think about the most typical equation of a line that you use. Y equals mx plus b. Okay, let's take that. So what are the parameters in that equation? M and B, exactly, right? Does that make sense? We can control those numbers, and by controlling those numbers, we can generate different lines. So we only require 2 dials. We got dialed in 2 numbers to create any line in the universe, right? We could write this in a different way. You remember going back to Algebra 1, do you ever remember writing a line in this form, where you write it as let's see. Well, I'm not gonna. We don't need 2. 2 for that, right? How many do you think are going to be required for a parabola, which is a slightly more complex function? 3. 3 are required. We're going to see that all year as we move along, and we talk more and more about higher level functions, about, for example, polynomials. Talk about polynomials. This is the simplest polynomial that we'll deal with. The next simplest would be a quadratic function. The next simplest would be a cubic function. I don't want to take time right now and define really tightly what a polynomial is, but you kind of get the idea. I mean, you're familiar with quadratic functions and a little bit familiar with cubic functions. And every time we step down and get 1 degree more complicated, so the order of the polynomial increases by 1. In other words, the highest power of x increases by 1. We have to have 1 extra dial to dial in that more complicated function, right? But the moral of the story is, for a parabola, whether we write it, there's a bunch of different forms we can write a parabola in that we'll do later in the year. Here's one of them. What are the parameters? A, B, and C. We could also write it like this. This is going to look familiar to you. What are the parameters? A, H, and K. Okay.
Wait, what?
Oh, that's supposed to be sorry, that's supposed to be a K. Bad K. Let me do it again. That's pretty bad K, admittedly. That's a great K. Okay, so A, H, and K, right? And that looks awfully familiar, I bet, right? What do you think the A stands for there? This is our, what we're going to call our vertex form of a parabola later in the year. You might have seen this in Algebra 1. What's A stand for, do you think? No. In this one right here, what do you think the A stands for in this parabola? What does it control about the graph of the parabola? Yeah, the amplitude, right? The vertical stretching. What's H control? Okay, so it's taking that vertex, which is usually at 0, 0 for our parent function, and it's giving us the coordinates of the x-coordinates of the vertex. In other words, how far was the parent function slid horizontally, and what is k? The y-coordinate of the vertex. How far the parent function was slid vertically, right? So the stuff we're talking about right now is going to come into play at a higher level soon, right? But once again, notice there are just these 3 parameters, right? So if we go back then to this list up here, this is kind of overkill a little bit for us, isn't it? For parabolas. We don't need all 4 of these, right? You get that? Is it wrong to use all 4 of them? Well, no. I mean, it works. We looked at an example yesterday. Remember where was this? Probably got lost in here somewhere. Yeah, where we did this, where we identified for this parabola, we identified its tweaks in terms of all 4 parameters. That was fine. It worked. We graphed it and it overlapped perfectly, right? We said that it was horizontally shifted by a certain amount, vertically shifted by a certain amount. It was flipped, so A was negative, right? Flipped over the x-axis. But then we said it was stretched horizontally by a certain amount and vertically by a certain amount because it was convenient, right? Because we started with a parabola. The normal parabola should have gone over 1 and down 1, over 1 and down 1. But ours went over, so that point that should have been, for a regular parabola, those points that should have been, you know, kind of there and there, well, they'd been moved. They had been moved both horizontally quite a bit and vertically they had been moved quite a bit, stretched, right? Does that make sense? And so we incorporated both of those stretches into it, which is fine. We got the right answer, but when we were done, where were we done? Right here. That looked a little bit complicated. So you look at all these numbers we ended up having. We ended up having a parameter there, a parameter there, a parameter there, and a parameter there, right? All these extra numbers. Did it end up being necessary? Well, not really, right? We should have been able to do it with just 3 parameters because it's a parabola. Only 3 dials are required. You see where I'm coming from? So this is one of the great things. The math gods are smart. The math gods, they communicated to us here in a way, if we just do algebra, that this was overkill. Because when we simplified this, right? When we went through the process of squaring the top and the bottom, well, the bottom became a 625. And then we just combined these 2 constants, right? It's just a fraction. And we simplified that into a single number out front, right? How many parameters does that look like now? 3. I've got a number out front. I've got a number there and a number there, right? Okay. What's the moral to that story? This is fascinating if you really think about this. It's amazing that it works this way. It just so happens that parabolas are the perfect shape so that this doesn't work for all functions. It would not work for a quartic function where the x was to the 4th power, or for a cubic function where x was cubed. It wouldn't work. But for a parabola, it does. It just so happens that because of the special shape of a parabola, stretching it vertically and stretching it horizontally are the same thing, right? That's not always going to work, though. That's really interesting and cool that it does work for a parabola. So by doing this algebra, the math gods communicated to us that, hey, we really don't need an A and a B. If we just simplify it, the math is going to work out so that I could express this as, for example, just an A, right? Because in this function right here, this is the number that's being multiplied by what's being squared, right? So that's the number that's out in front of the function. You get that? Does that seem pretty cool? I mean, it should, if you think about that. That's amazing that it does that, right? So all we would have had to do, instead of instead of our horizontal stretch and our vertical stretch, our big horizontal stretch and our relatively small vertical stretch, all we would have had to do instead is one vertical compression. And that would have accounted for both of those at once, right? So now that we know that we don't require both a stretch, horizontal and vertical stretch, how could we, for example, approach this problem right here? This is kind of what we talked about at the end yesterday, but I felt like it just got thrown in at the end. How could we do this problem maybe in an easier way? How many parameters, if we want to make this easier, how many parameters do we probably want to use? Three, right? Why not just pick 3 at the beginning and fit this data to those 3 parameters instead of the 4? Now, would it work to do it the other way? Yeah, we did it, right? I mean, it did work, right? We used 4, and then we just combined 2 of those algebraically into 1. Agreed? But we don't have to do it that way. We could just pick 3 and use those 3, right? So what if we discard the B? Let's just keep the A in there, because typically later in the year, that's what we're going to do. We're not going to ever use this B for parabolas. We're just going to use the A, right? So then all we've got to start with is g of x equals A times the quantity, we get rid of the B, times f of x minus h squared plus k. And for us, what's our parent function? X squared, right? So don't lose sight of that. Our parent function is x squared. So if f of x is x squared, what's f of a? A squared. What's f of x minus h? X minus h. Oh, I wasn't supposed to put that there anyway. Whoops. Right, you get that? That shouldn't have been there. It's just f of x minus h, which is x minus h quantity squared, right? So this is the exact function we're fitting. G of x equals a times f of x minus h, which is just x minus h squared plus k. Right? So what are they? What do we know? How far? Let's do the easy ones first. Let's do the ones that we can spot by inspecting the graph. How far has this thing been shifted? Our parent function been shifted to the right? 3. So positive 3, right? So which one of those am I naming? H. So h equals positive 3. What's k? How far has it been shifted vertically? 3. Positive 3. So those are done. What's a? Well, we don't know. Right? A isn't immediately obvious, is it? Right? But we can solve for a. We can solve for a because if we know 2 of these parameters and we know some points through which the curve travels, each one of those points is a solution, right? And sometimes we throw these words around and we lose sight of their special meanings. What is a solution? What's unique about the point 8, 4 with our function?
It's a solution.
Okay, it's a solution, but what's that mean?
It means that it works in that function.
It works. It means that if I plug in an x value of 8, my function is guaranteed, has to, spit out a y value of 4, right? So that's an x and a y value that have to work. So that's one of 3 examples that I know that I could just plug in. Get it? Okay? Right?
Okay.
So now if I plug this stuff in there, let's see where we are. So now we're at the point where g of x, which is really just y, right?
Yeah.
G of x, same thing as y, equals a, which we don't know, times the quantity x minus 3, right, squared, plus 3, right?
Yes.
So now I should be able to plug in any x and y value I choose. However, there's one exception here. One of them is not gonna work. Which one? The vertex. If I plug in 3, 3, I'm gonna get a problem. If I try to plug that in, 3 goes in for y. And it's interesting why this doesn't work. I'm gonna see if you can tell me. Well, so all that tells me is 3 equals a times 0 plus 3. In other words, 3 equals 3. Well, duh, right? You know that. How come that one failed us? Any ideas? Okay,
There was infinitely many solutions.
well, okay, true. But there's something about this point that's already, we've already kind of used that point in a way, haven't we?
Yeah.
How did we use that point?
That was
For h and k, right? And so because that one's already been used for h and k, the math gods prohibit us from using that to find a. Because really, that doesn't count as a point then, right? It's not, the point itself is just giving us the h and k values. We need some point other than the vertex that we could plug in, okay?
Do we have to do that for every equation? Use a point other than the vertex to find a?
For every parabola, you will, yeah. Mhm. And that'll, once again, you'll get extra insight into that. I know I say this a lot, but when we start talking about this, when we focus on parabolas, that'll become really clear why that's the case, okay? So we have to use a different point. Well, which one? How about if we pick, this one's got a little bit smaller numbers, just pick that one instead, okay? So let's try that one. Okay, so let's try that one then. If I use this guy right here, that's going to give me what? So I'm starting off with y, which is 4, equals a, which we're solving for, times, what's my x value? -2 minus 3 squared plus 3, right? So now all I have to do there is just solve for my one unknown, which is a, right?
Yeah.
Everybody get that?
Yeah.
Okay, so isn't that easier? If we just start with 3 parameters, we can always find h and k really simple by just looking at where the vertex has been slid. Pick an x and a y value that are a solution other than the vertex, and I can use that information to solve algebraically. I don't have to look at the graph to do this. I can just do the math and figure out what the value of a needs to be, right? So quickly, let's just do that. What do we get? This is a 4 equals a times, what's -2 minus 3? Squared? So what are the 2 steps in order to solve for a? What do I do? Subtract 3, which gives us 1 over here, right? Then divide by 25. So a equals 1/25,
No. Yes.
right?
What?
If I subtract 3, I get 1
Yeah.
divided by 25.
Um,
Okay? So then my final version of this function is just g of x equals 1/25 the quantity x minus 3 squared plus 3.
Oh my gosh, it makes so much more sense because last night I just guessed on all of them.
Yeah, that's gonna take you, there's only an infinite number of choices, so that,
because I added 3 to 25.
Yeah, that's right now.
I added 3.
okay, yes ma'am.
How many retries are we supposed to have?
Okay, I don't really understand this.
Because I get, that way, where you get, then it says, oh, you can't retry anymore.
I know, and it gives me a bunch of retries if I just go through examples.
Okay, so I think what it does, the only setting I can control on that, I always give you unlimited attempts on the assignment. That means you gotta start the whole thing over. That's not very good. The only thing I can control is I can give you 10 regrades, and I think what's going on, as best I can tell, is that means you can retry 10 total things on the whole assignment, right? So what I'm gonna do in the future, to make that, because personally, you know what I would like you to be able to do is have unlimited tries on every problem. So what I'll do is I'll just make sure I break the assignments up into, like instead of doing maybe 2 bigger assignments, I'll do 4 smaller ones. And so that way you get your 10 retries spread over only like 2 or 3 problems. Does that make sense? So
Unless
that's,
you're a dumb
I'm still trying to figure out how to best do this too.
Don't be looking at me.
Like, Sometimes they also give you the option to get
Yeah, but it wouldn't even let me do that.
Yeah, but after a while, then you
Yeah,
just
after a
stops you from
while.
doing that, which I wish it wouldn't do that. My feedback to them is gonna be, you need to have an unlimited on there, because.
You need
what's-
to limit it, you should just go to Moodle.
No, we gotta give this, really, I mean, it's not, you know how I feel, but I'm a part of a bigger picture here. Okay, here we go. So here's my question though, now, listen please. So now hindsight is always 20/20, right? Now that we know the answer, right, we know that the value of A was 1/25th, let's look back and just for future reference, could we have predicted that and how? Look at this picture up here and tell me if you can look at that and say, oh, okay, I could have seen that before. There's something about that that sort of gives it away. What do you think, Sam?
It goes up one Y value every 5.
Ah, okay, yeah, look at this. So now, normally, let's think about a regular parent function. The parent function, if this is the vertex, on the parent function, if I go over 1, well, 1 squared is 1, so I go up 1, right? Does that make sense?
Yes.
Back 1, I go up 1. If I go over 2, how far up should I go? No. 4. 2 squared is 4, right? It's a parabola. So I'd go up 4, and so on, right? If I go over 1, 2, 3, 4, 5, how far up should I go? 25, right? I should go up
And it's only one of the 25 that is.
25, but I only went up 1. So, see what I'm saying? So this must have been compressed by a factor of 1/25th, right? Or compressed by a factor of 25, meaning I multiplied by 1/25th, right? It's been squashed down 25 times further than it would normally be, right? So you could look at this and figure it out by inspection. What would it be? What if I had one like this? What if I had a parabola, let's say, regardless of where the you don't even really care where the vertex is. That's just H and K, right? How far it's been slid. But once we get to the vertex, let's just say that the vertex, when I go over 3, I'm going down 2. So that's a point right there. Can anybody tell me what the value of A is for that without having to go through that whole process?
2 9ths.
It's 2/9. Negative 2/9, right? Because it got flipped. Everybody see that? Because it should have gone, when I go over 3, the point should have been down here 9, right? But it was only down 2. See that? Okay? Make sense? Okay. All right. Good. Okay, so lab day tomorrow. What I want to do today, I want to talk to you about one other thing, that comes up on your assignment. Did you guys get any questions about even and odd functions?
No.
Okay, you got 1 or 2, right? I think. On maybe the 1.3.1 assignment? Okay.
Oh, yeah, that's the one that.
All right, so let's talk about this for just a second, because this is something that, once again, we're going to see, not that it's very hard on this assignment, but we're going to see this all year. So I want to take this opportunity to kind of really make sure you understand what the meaning of an even and odd function is, because this is important. So what's our test? How do we define an even function? What's the behavior of an even function?
2, 4, 6, 8. Both sides are symmetric.
Okay, so we're going to get into the symmetry stuff, but if I input negative x into the function, what's the output going to be? No. So this, I'll just show this to you. So this is the test for an even function. If that happens for any value of x I choose, then it's an even function, right? Let's take an example. What if we have, for example, let's take the function f of x. I don't know why it does that. F of x equals, how about x squared plus 3? Okay. This is the test I would apply to see if it's even. So we're going to start with, we always start here, and then we see if we get that result. Okay, so let's try that. if I take this function and I plug in negative x, so f So if I plug in negative x, that's what I get. Now, how does that simplify? What can I do to the right side of this to make this easier? What is negative x quantity squared?
X squared.
It's just x squared, isn't it? Right? Everybody agree? Okay. So this gives me and isn't that just f of x? See what I'm saying? So f of minus x ends up equaling f of positive x. So it's even. Okay? What about an odd function? What do you suppose the definition of an odd function is going to be then?
Negative x is not equal.
Okay, but it's something more specific. It's equal to the opposite of f of x. Okay, so let's try one like that.
Why do they call it odd and even?
You're gonna come up with that on your own.
I don't.
Here was one example that was even, right? So let's try this one. Let's try, how about f of x equals x cubed minus 4x. Let's try that one. So now if we input f of negative x and we get back minus f of x, that proves that it's odd, okay? So in this case, f of negative x would equal negative x cubed minus 4 times negative x, right? Everybody agree?
Yeah.
Okay. So what happens if I simplify this side? What do I get? What is the first term? What's the quantity negative x cubed?
Negative x cubed.
Okay, it's the same thing as negative x cubed. The quantity negative x cubed is equal to negative x cubed, right? How come? Can you defend that? I know you know the answer to that, but how could you prove that?
Because it's negative 3 times and negative 3
When you
times.
times a negative by a positive.
Let me ask you this. What is the quantity 2x cubed?
Eight.
8x cubed, right? How did we get that?
Math.
Because I'm able to do this. If I have a product to a power, can't I write that as the product of the powers? Right? So in other words, in general, a times b to the m equals a to the m times b to the m, right? And you intuitively know that, I think. So I could write this as 2 cubed times x cubed, which is just 8x cubed. So what are the two numbers here that are being cubed? Negative 1 and x, right? So negative 1 cubed is negative 1, x cubed is x cubed. So this gives me negative x cubed. What about this? What's negative 4 times negative x? Okay, so now we've got to connect this to this. What's the last thing I could do? Sam?
You multiplied the top equation by
Okay, but you gotta be careful with that. I can't just go multiplying, willy-nilly. I can't just go multiplying equations by negative 1 because that changes them, right? I don't want to change the identity of the function. I want to preserve the identity, but just write it in a different form. There's really only two things I can do when I want to preserve the identity. I can multiply by 1, or I can add 0, or maybe I can just even factor things, break things apart, which is what we want to do here. Is there anything I can factor out of both of these terms? Remember back to Algebra 1, we're going to do a lot of factoring this year. Factoring just means dividing, right? Is there any term or any factor I could divide away? I could undistribute from each of those to make it look like, so I can see that function popping out. Negative 1. Sure, what if I divide away a negative 1? Then I've got negative, and I don't even write the 1. Just implied it's a 1, right? It's there. I'll make it kind of invisible. There it is. -1 times, well, what's left over if I undistribute or divide away a -1? Well, what's negative x cubed divided by -1? X cubed. What's 4x divided by -1? Okay, right, you see that? Well, isn't that right there just f of x? Right, so then what do we got? So we've just got negative f of x. So it's odd. Okay? One more example. Let's try one of these now. Let's look at, how about the function f of x equals 2x cubed plus 3x squared minus x. Okay, so what do? You want to test to see if it's even or odd? Yeah, we're just going to evaluate it at -x and see what happens, right? If one of these two things happens, then it's either even or odd, right? Okay, so let's try it. Okay, so everybody agree? That's what we're going to do. We're going to simplify that and see what the result is. And all the dust settles. What do we get? What's 2 times -x cubed? Okay, we okay with that? How about 3 times -x squared? So -x squared is just going to be -1 squared times x squared. What's that? No. What's that part? What's -x quantity squared? Just plain old x squared, right? Because -1 squared, any negative number to an even power is positive, right? Okay, so that's going to give me plus 3 times x squared. And then minus -x plus x. Is that ever going to fit that? Okay, so would you agree that this is not the same as that, is it? So f of -x is not equal to f of x. But even if I try to factor out a -1, look what I get. That's going to become positive, right? That's going to become negative, and that's going to become, well, that still doesn't fit, right? This in here is not that. So what do we say about this one? It's neither even nor odd, right? Okay, but what do you think? You've seen 3 examples of this. Could you give me an example of a different function that was even, you think?
Yeah.
What's it going to be? What's the part of this process that made, if we go back, I erased that first one, darn it, but what's the part of the process that made this function even? When I substituted in a -x, how come all the negatives went away?
Because it's x squared.
Okay, because x squared, and there's actually an invisible x to the 0 there, right? Because what is anything to the 0? 1, right? Okay, so what if I made the function, I want you to make a prediction for me here. What if I made the function even or odd?
It's even.
It's even, right? Because all the powers of x are even numbers. 0 is even, isn't it? Agreed? 0 fits the pattern for even. So anytime I plug in a -x, taken to an even power, the negative sign is just going to go away, right? Everybody see that? So where do you think then the name even comes from? Yeah, it comes from if we write a polynomial function out, and those are really common functions for us to use in math. If we write out a polynomial, if the polynomial has only even powers of x, you don't even have to do anything. You can just look at that and say, oh, they're all even, so it's an even function. And then by contrast, what's an odd function going to be? All odd powers of x, right? Now it works for other functions too, and we'll get to that. Are we out of here at 45?
Yeah.
Okay, so
4 minutes of fun.
that's fine. 4 minutes, we can do it. 4 minutes, plenty of time to learn lots of math. So what's going to be? Let's look at one more thing here. Let's look at what the ramifications are of this if we think about symmetry. Okay, let's not even pin ourselves down with a specific function, but we're just going to say we've got some even function, and here's the behavior, right? F of negative x equals f of x. I don't even have to know what the function is. I can just pick a representative value of x, and that behavior would have to work for all of the infinite x values in the function, right? So we'll just pick one of them to demonstrate what they all have to do. Okay, so we'll make this one red. So let's just say, hypothetically, let's make these, how about these are ones right here on this graph paper. Let's say if we go over by 2, we're going to go up by 3. Okay, so in other words, the coordinates of that point are x, f of x, right? Everybody agree? Well, this tells us that f of negative x is equal to f of x. In other words, if I go back x, which in this case is 2, right? So technically, I guess this is 2 f of 2, right? What if I go backwards 2? So that means I'm putting in a negative x. Well, if it's an even function, that tells me that the height has to be the same as it was for the positive 2, right? So if I go back 2, I also have to go up that far, right? So generally speaking, this is the point negative x, f of x. Specifically, it's the point negative 2, f of 2. Well, what kind of symmetry do those 2 points have with respect to each other? Same y value. So how can we describe that? If I strung together an infinite number of those, maybe there's going to be a point like there and a point like there, or something like that. So maybe it looks like this. What kind of symmetry, if I take all those pairs of points together, they all have the same y values, how could I describe that symmetry? It's a reflective symmetry, right? Or folding symmetry, whatever you want to call it. It's line symmetry. About what line?
Y-axis.
The y-axis, yeah. So even symmetry is reflective symmetry about the y-axis always, right? Okay, you guys better... Yeah, this class needs to be a little longer, I think. I don't like this. I gotta talk to the principal about that.